The area problem is one of the two important things that we learn about in calculus, important motivating problems, the distance problem, the area problem, the tangent problem. Well, so if you remember, the question is, if you have some sort of random shape, what's the area of the random shape? Well, you don't really know. Now, we know how to find the area of some shapes, right? We know how to find the area of a circle, it's pi r squared. We know how to find the area of a square, right? We know how to find the area of a triangle. If we have some sort of random polygon, let's draw a random polygon, there we go. We can find the area of this because we can easily break it up into squares or triangles or, you know, whatever you want, whatever you like. How about that? That looks fine. So you could find the area of this by using this method of breaking it up into triangles. We're gonna kind of want to do the same thing with this shape here, but you know, you can't really break it up as a triangle because it doesn't have, the sides aren't straight. So Newton and Leibniz, though, kind of thought about it in the way like, well, if we can break it up, sort of break it up, let's show you. Let's see if we can break it up. All right, let me just kind of break it up. How about that? Well, that hasn't helped me very much at all because all of the sides are not straight still, okay? But I can perhaps make some sort of approximation, and because I like squares or rectangles, rectangles are easy, right? So let's just make them rectangles. Let's make them big rectangles so we have like an overshoot. So I'm kind of just going to make these some kind of rectangles here, like this. So although I couldn't figure out the area of this weird shape, I can figure out the area of these rectangles, right? Because I can measure those sides. All right, so I have an approximation of the area of my weird shape. It's an over approximation because my rectangles are bigger, okay? And it's not a particularly good approximation, right? I mean, it's all right. It's not great though. The idea of the area problem is that to notice, well, if I make the rectangle smaller, I get a better approximation. Just right here, for example, if instead of being this rectangle, let's make it a smaller rectangle, let's cut it in half, right? Then I lose a bunch of that overshoot. Now this part is a little bit of a better approximation. So you can imagine, okay, now I'm going to cut all these rectangles in half. I'm not going to bother to draw, it takes too long. But this is the idea, right? If you were going to cut it down, you're going to get better and better approximations. Well, this idea was, well, let's put an infinite number of rectangles, okay? They're going to be infinitesimally small. And as I get more and more rectangles, I'm getting closer and closer to the actual area of the shape. So it's a limit, right? You're going to take the number of rectangles to infinity, the length, the width of the rectangle is going to go to 0. It's a limit. You're going to do a limit. You're going to be able to find, ideally, the area of this shape. So really, to make it a little bit nicer, what we want to do, perhaps, instead of just this weird shape that I don't even know what it is, let's use some function. Let's say we know what the function is. And we're going to go from A to B. And we're going to do this rectangle process, okay? I'm not going to spend too much time drawing it on here because we can draw it electronically. It's so much nicer. But just to get the idea, We'll just go right ahead. And this is actually a GeoGebra worksheet, which I can, I will put up for you guys. Okay. Let's move myself. See it? Okay. So in this particular example, and we're going to change all these parameters just because it's kind of fun. But in this particular example, this is the function that they're using. Just going up like this. And they've chosen from -4 to 8. Now you can change everything in this thing. So we can change it if we wanted it so to -6. And it goes to -6, right? And they've chosen a particular number of rectangles just for the picture, right? There's 12 rectangles. And so they've taken this, and they've broken it up. And then how high are the rectangles? That's another thing, right? I did mine on this example as an overshoot. You can see what they did here is they chose the middle point of the of each interval. You're going to take your big interval from A to B. Here we did from a -6 to 8. And you're going to break it up into a certain number of rectangles. And then, so you're just going to take the delta x. The delta x is the distance there. Now let me make that back to 4 so that we have something nice. Okay? So now that, of course, the numbers work out a little bit better, I'm just showing how you can change it. So in this case, because it's the distance of length 12, right? So if I break it up into 12 rectangles, the width of each rectangle is 1. That's what we're calling delta x. The height of each rectangle now is going to be whatever point we choose for our function. And the thing is, it can be anything. You'll get a slightly different answer because depending on what point you use, if you're just adding up the rectangles, as we will in section 5.2, just kind of do a couple of them. But in the limit, it's not going to matter. So what do I mean about that? So what I mean is, and they have it right over here. Let's see if this works. So this here is their chosen left endpoints, right? So for each one of these intervals, you choose the left endpoint of the interval and you go up there, and that's the height of your rectangle. So you see how that's all going to the left. So here there's overshoot, and here there's an undershoot, whatever, right? So that's the left. That's the midpoint. And we could do right rectangles as well. Now, you'll notice if I do left or right, there was a rectangle kind of missing. Not really missing. What's happened is because you're using that 0 point, it's in there. It's just going to be, you're going to be being multiplied by 0. Okay, so that can happen. Not really a big deal. Okay. What I wanted to show you, that was one thing. Okay. Now the other thing is, what are we really doing? So you can see, this is the actual answer of what the actual area is. If we can compute it with calculus, which we will be able to do, and you probably already know how. But this is the answer, right? That when they added up these 12 rectangles. Now let's say if we add more rectangles, let's pull it off. Oh, that's a lot of rectangles. Okay. So if we have 499 rectangles, they're too small, you can't really see them. At that point, I didn't want to go that far, but you see it's pretty close when you've got like 500 rectangles. What I wanted to do, you know what, it might work better with this pen. Okay, so what I wanted to do was sort of something like that. Okay, so you can see we started out with the 12 rectangles. It wasn't super great. Now we've got twice as many rectangles, and you can see how much nicer already it's doing, how well it's doing. Maybe we can pull it a little more. So, and there, for example, so stuff like that. So this is actually a cute little tool just for visualizing. So as I said, okay, we can change the function. You can change the function in here, right? So we can just type whatever we want. Let's say we want to do x squared plus 3. Okay. And maybe I don't need all those rectangles. Let's put down just a few rectangles a little bit better. And let me change this so it's a little bit easier to see. What about if we do minus 3, 3? Okay. Okay, so that maybe a little bit better. You know what? It's still not that great. Let's change this. We can zoom in, I think, as well, but it might be better just to do minus 2 to 2, just so that we can see it a little bit better. Okay. No, I wanted to. Well, you get the idea. So you can play with this. This kind of nice. Do a few less rectangles. So one rectangle, right? That's sort of limiting. And you can see whether you're going to do left endpoint, right endpoint, whatever. Midpoint. The midpoint is a little bit better. You know, typically not hugely better, but a little bit better. There are also, as I said, we can do any point. So, and it doesn't always have to be the same point. Like I could do the midpoint over here and the right endpoint over there, or whatever I want, right? I could find the lowest point. So, and that would give me an underestimate, and I can always choose the highest point, and that could give me an overestimate. I'm not going to worry about any of that for this particular part of the class because it's just, all right. So this is kind of fun to play with that. And you see, for this particular example, unlike the one with the sign, we've done really well here with just 4 rectangles, right? Look, 17 and 17.3, that's pretty close. So depending on the function and the numbers, you'll need more rectangles or less rectangles. But we're not really going to worry about Riemann sums too much. Okay, we're just going to move it into the integral. Right.